All right, welcome everyone to the Fox 2020 tutorial on Indistinguishability Obfuscation from Well-Founded Assumptions. And this is the result of a really wonderful collaboration, multi-year collaboration with Ayush Jain and Rachel Lynn. So let's get started. Suppose for a moment that you want to keep a secret, but unfortunately for you, there's an adversary that has captured your entire brain. It's ripped your brain out of your skull, keeping you alive in the process. And it is able to read and tamper with the activity of every single neuron in your brain. It understands exactly what's going on, where every electron is going. And, and in fact, while it has captured your brain, you're supposed to keep thinking about your secret. And nevertheless, we ask the question, is it possible for you to maintain a secret in the face of this type of mind-reading, mind-controlling adversary? Is that somehow possible? And indeed, this seems almost crazy, impossible to achieve. And thankfully, this doesn't happen in real life. I hope it never happens to you. I've never heard of it happening so far, thankfully. But if you think about it, the computer science analog of this situation is actually ubiquitous. The computer science analog of the scenario is where we replace your brain with a computer program, right? Because a computer program instructs a computer exactly what to think, how to think, what process to use in thinking about whatever it's going to think about. And we can ask this question, which is that if a computer program is in fact captured by an adversary, which happens all the time, right? And in fact, in many cases, we just give away our computer programs to an adversary. An adversary can buy a program, off the internet or in a big box store, and then can see exactly what's going on inside that program. And we ask the question, is it possible for a computer program like that to actually keep a secret within itself and use that secret, even though the adversary actually has complete access to the computer program? And I want to emphasize, we're talking about a situation where there's no trusted hardware, there's no interaction, everything about the computer is known to the adversary. The program doesn't get to talk to some external computer over the internet. It's just running on ordinary hardware. And it's an ordinary program. It has plain inputs and it produces plain outputs. The adversary can provide whatever inputs it likes. You can then tamper with the program as it outputs, as it creates an output, and you can see what the output is that the program creates. And again, this is running on a single, completely ordinary off-the-shelf computer. So this is the problem that we want to study. This is the problem of program obfuscation, which is a really challenging situation, and one that is quite different from almost every aspect, almost every notion in cryptography that we've studied before. Indeed, the most closely related concepts in cryptography to program obfuscation that have been studied classically are the notions of secure multi-party computation that were proposed by Yao, Goldratt, Macaulay, and Wigderson, Benner, Goldwasser, and Wigderson, and then over 100, many, in fact, hundreds of works that have followed up on these notions. So how is that different? That also talks about hiding a secret that is being operated on in a computational manner, but it's different in the following fundamental way. So the analog would be that we take this brain that is thinking about a secret, and we actually subdivide it into many different portions. And now in secure multi-party computation, an adversary gets to see and tamper with one part of that brain, or in the most advanced form of secure multi-party computation, it can see and tamper with almost all of this brain, but there's still going to be one portion of the brain that is completely blocked from the adversary. So the adversary has absolutely no idea what is happening in that part of the brain, and that part of the brain is continuing to operate normally. So this is the notion of secure multi-party computation that has been studied for decades. And if you think about it, if we know that the adversary is blocked from a certain part of the brain, then there's a natural solution concept which has been explored over the many decades, which is the idea to kind of spread out the computation, spread out the secrets among all these different parts of the brain in such a way that every part of that secret is needed in order to reconstruct the overall secret. This is the notion of secret sharing that has been well explored in cryptography. And again, it's a wonderful area. There's a lot of beautiful work that's been done in this context, but it is fundamentally different from program obfuscation. Because again, this concept and all the other previous concepts basically required some portion of the computation to be completely hidden from the adversary. Whereas in general purpose obfuscation that we're looking at, no part of the computation is actually kept hidden from the adversary. So this notion of obfuscation is a very challenging one. It's completely different from what's come before. And back in 2001, in a joint work with Barak et al., we proposed a concrete, specific formal notion of obfuscation that we called indistinguishability obfuscation. So in indistinguishability obfuscation, we have I/O, which is a probabilistic polynomial time algorithm. You can think of it as a kind of compiler that takes in input a program and produces an output as output another program. And we have a few basic requirements. The most basic requirement is that for any program P, I/O of P produces a program that is equivalent to the original program. So it has the same input-output behavior as the original program. And again, for this talk, we're going to think about programs as just being objects that compute functions. So they take an input and produce an output. Okay. And furthermore, the requirement is that the running time of the obfuscated version of the program of I/O of P is at most polynomial in the original running time of the program. So there's at most a polynomial slowdown that is incurred by means of obfuscation. And then finally, we have the security property. And the security property says that if we start with two equivalent programs, P0 and P1 of the same size, then no polynomial time adversary can distinguish between the obfuscation of P0 and the obfuscation of P1. And that is true even if it knows the original two programs, P0 and P1. If it sees the obfuscated version of P0 or the obfuscated version of P1, it has no better than essentially a random chance of guessing whether the obfuscated program came from P0 or came from P1. Okay? And this is a well-defined notion. It's a very precise, easily formalized definition of security. And before we move on, I want to give you some intuition as to how we should think about this notion of indistinguishability obfuscation. One way to think about it is that I/O is basically a pseudo-canonicalizer. What it does is it produces a obfuscated program that is indistinguishable from, and therefore reveals nothing more, than a canonical form of the program P. In other words, if it was possible to take a program and just find some canonical form, so that no matter what equivalent formulation of that program you had, you always wind up with the same canonical form, then that would obviously satisfy the definition of indistinguishability obfuscation that we have posed here. The only difference between our definition of I/O and a canonical form is that the output only needs to be computationally indistinguishable from this canonical form. So you just can't tell which program you started with. And this is quite interesting because one of the consequences, sort of a curious fact, is that if P equals NP, then we know that the polynomial hierarchy collapses. And in that case, suppose we implement a program by means of a Boolean circuit. What we could do is, in polynomial time, because P equals NP, we could simply calculate the minimum equivalent circuit to C. In other words, for example, the lexicographically first circuit that is equivalent to C, and output that. And of course, this would satisfy the definition of I/O because any two equivalent circuits would yield the same canonical form in the form of this minimum equivalent circuit. So indeed, if P equals NP, then I/O exists. And that's a little different, a little unusual for cryptography, because typically if P equals NP, then sort of cryptography falls apart. We can't have, for example, public key encryption if P equals NP, right? But nevertheless, IO is an object that actually does exist even if P equals NP, which is interesting. Of course, if P equaled NP, then IO would exist, but we wouldn't be able to do very much with it, unfortunately, as a cryptographic tool. But it's still just an interesting observation that IO exists even if P equals NP. All right, so great, we have a definition. It's well defined. It can be made completely precise. So why should we care? Well, again, honestly, I think the reason we should care is because it's such a fascinating notion, but it actually turns out to be incredibly useful as well. So if we think about cryptography prior to sort of the exploration of IO, it's a beautiful area, many, many amazing concepts that have been studied for for decades, in fact, centuries in some sense, but for decades in modern cryptography. But then once IO was introduced, especially when armed with a technique called punctured programming that was introduced in a joint work with Brent Waters back in 2014, it turned out that IO just had an amazing number of consequences. And I've just put a few of these on this slide right now. Really, it would take an entirely new tutorial to show all the many, many different applications of IO. And indeed, there have been well over 100 papers that have been written showing how to use IO to build interesting new cryptographic objects. And indeed, in this way, IO isn't just a cool, yet another cool cryptographic notion. It actually expands the scope of cryptography. There are problems which weren't really even seen as being in scope for mathematical cryptography that have become in scope because of the power of IO. And indeed, it even goes in the other direction. So it turns out that armed with this powerful notion of IO, we've actually been able to go back and look at classical cryptographic primitives, for example, signature schemes and non-interactive zero-knowledge proofs, and show how to do them in much more powerful, much more efficient ways because of IO. So once again, this is not the subject of this tutorial. Our subject is going to be how are we going to actually build this notion? How are we going to build IO? So let's take a step back and just think about this from sort of a historical perspective. If we think about the problem of constructing IO, again, I told you that it was defined all the way back in 2001 in our joint work with Barak et al. But for over a decade, really nothing was happening. So if we look at published papers on potential constructions of IO, there is just nothing. There are no published papers showing how to construct IO in any form. And of course, what that lack of publication actually indicates is that there's a graveyard of unpublished ideas that didn't work. And I can certainly personally attest to many of these tombstones of ideas that I tried that didn't work. And of course, I'm sure there are hundreds of others, or at least dozens of others, who tried and weren't able to make it work. And actually, to make matters worse, that original paper that I mentioned with Voss and others, and in fact several follow-up papers, in fact showed impossibility results for a number of related notions to IO. In fact, the main focus of the paper with Voss and others was actually to show impossibility results for other notions of obfuscation. IO was proposed there as sort of a way to escape these impossibility results. But again, for well over a decade, we just had no idea how to go about constructing IO. Then there was suddenly some optimism because back in 2013, in the joint work with Garg et al., we used a new cryptographic primitive called cryptographic multilinear maps, which I won't define because it's not actually relevant to this tutorial. But we were able to show how to use this new kind of pretty complicated algebraic object to build IO. So this is the first mathematical approach to constructing obfuscation. And as an assumption, it was quite complicated and definitely new. But we had been reasonably successful in cryptography and making new assumptions, and so maybe it was okay. Unfortunately, that optimism did not last, and just within a few years, um, there were a number of weaknesses that were discovered in cryptographic multilinear maps. And then in a joint work with Miles and Zandri in 2016, we actually showed how to attack not just the multilinear maps, but even the specific IO constructions that were proposed. And that was further followed up on by Upon et al. Um, in quite devastating attacks on existing IO schemes. Now, after that, again, in a few works, joint with Badri Nayan et al. And Garg et al., we were able to relax that and show that a weaker model of cryptographic multilinear maps are also sufficient to produce IO. And again, as an assumption, well, it's a new algebraic model. It is fairly complicated, but it does seem to avoid attacks. And so that was some reason for optimism. But at the same time, it was quite far from our objective, which is to really build IO from well-founded, well-studied assumptions. It was completely new, and it was pretty complicated. Now, it is the case that, in fact, still 4 years later, there are still no attacks known on those schemes for suitable, suitable settings of parameters. However, again, it's a new notion, a new algebraic model, so still far from sort of a comfortable situation. There was another line of work that began with the seminal work of Ananthan Jain and Vitansky and Vakunthanathan that showed how to transform a notion called functional encryption into IO. You'll hear more about that later in this tutorial, followed by a breakthrough work of Lin back in 2016 and several follow-up works that culminated in some work that showed how to use degree 3 cryptographic multilinear maps. I haven't told you exactly what that means, but roughly it corresponds to only needing to evaluate degree 3 polynomials in a certain private way, together with some well-studied assumptions, PRGs and NC0 and the learning with errors assumption. I'll again talk more about these momentarily. But by combining these things, again, we were able to show that IO exists. But again, unfortunately, it turned out that these degree 3 version of cryptographic multilinear maps were actually no more secure than the general notions of cryptographic multilinear maps. And so all the candidates for these underlying assumptions were essentially broken in these works that came up with new algebraic attacks. And so again, it's not a satisfying situation. At the same time, we should keep in mind that the assumptions themselves were actually simple to state in the language of these degree 3 multilinear maps, but the candidates themselves were unfortunately broken, so there was no instantiation of these assumptions. Okay, so what happened next? So what happened next was that there were another sequence of works that came along that introduced yet another new notion. This was a type of degree 2 computable pseudorandom object, okay, which again, I won't go into the details of, but they were, earlier works of also that we were involved in showed that such objects, together with well-founded standard assumptions, would imply IO. And again, there was some optimism about that. But once again, all of these candidates, all the candidates of this new object, degree 2 pseudorandom objects, were actually broken by means of the sum of squares paradigm in a sequence of works by Barak et al. And Lombardi and Vakunthanathan, and another joint work with Barak et al. And this was also quite fascinating from a theoretical point of view, because the sum of squares paradigm and sort of classic semi-definite programming-based optimization techniques had never been used before that for effective cryptanalysis of sort of interesting cryptographic objects, but they were used to unfortunately break these new objects that we were trying to make use of to build IO. So once again, it seemed that our sort of hopes were dashed. And quite honestly, around this time, uh, there was considerable skepticism and some pessimism that started to, pop up in the community. And some people felt like they'd been burned sort of one too many times. And in fact, a collection of authors including Alison Bishop and many others, who had all worked on obfuscation, devoted years of their lives to constructing IO, published a note called "In Pursuit of Clarity in Obfuscation," basically lamenting the state of affairs and how little we seem to understand how we can securely construct IO. So at this point, things were definitely looking a little grim. And I remember I was preparing a talk around this time in 2017, and I came across this wonderful article that was published in Nature, excuse me, by the physicist Steven Weinberg, in which he wrote, uh, quote, "A student told me that he wanted to go into general relativity rather than the area that I was working on, elementary particle physics, because the principles of the former were well known, while the latter seemed like a mess to him. It struck me," Steven Weinberg writes, "that he had just given a perfectly good reason for doing the opposite. My advice is to go for the messes. That's where the action is." And I love this quote, and I think that it really applies quite well for constructing IO and the need for us to sort of tame this wilderness. And I think this kind of advice is actually particularly useful in the context of the StockFox community. Because let's face it, most of the work that we do in the StockFox community is quite different. We love getting the optimal result, reducing the complexity of some algorithm, or formulating or improving some, well specified complexity theory conjecture. And here the situation is just different. We have a clear target that we want to build, but what ingredients are really needed to build it, it was really quite unclear. And in this way, it's just sort of much more messy and much more of an untamed wilderness. And it can seem often that it's just unclear sort of what are the rules of the game, how do we know that we have a result. And indeed, one of the talented graduate students that I worked with once told me that, look, Amit, I'm sorry, I just don't want to work on constructing IO because I don't know what to do. And can you please just give me a conjecture, a well-defined conjecture, and then I can try to prove it or disprove it. And unfortunately, we just weren't in that sort of situation when it came to constructing IO. And nevertheless, of course, taming these messes um, is essential, right? This is absolutely our job as theoreticians. And I think, for me, reading this sort of sage advice given by Steven Weinberg, um, lets us sort of reflect and see that actually we do know what we want, right? What we want is deeper understanding. And even all of these failures, all of these breaks and new algorithms that we looked at to break assumptions, they all gave us an understanding of what are paths not to pursue, what are the weaknesses that we need to avoid when we're thinking about how to build IO. And moreover, even if the frameworks that we had come up with didn't have a concrete instantiation that would allow us to get all the way to building IO, they were still very useful and interesting and intriguing frameworks that we could explore to try to understand things better and to try to tame this wilderness. And of course, I'm here speaking to you, and so obviously it did work out for us. Um, but I wanted to take this opportunity for us to sort of reflect in the StockFox community on making sure that we also work in these kinds of messes to try to tame areas where we don't really have a good theoretical understanding whatsoever, and where it's not even clear what the conjecture should be. So what happened next, historically? So after those unfortunate breaks of degree 2 pseudorandom objects, in a sequence of works, we propose yet another new object, a new, what I'll call leaky pseudorandom object, which I'm going to elaborate on a little bit more in this part of the tutorial, and you'll hear much more about in parts 2 and 3 of this tutorial. And we were able to show that these new leaky pseudorandom objects, together with some well-founded assumptions that have been studied for a long time, are actually sufficient for I/O. And again, this as an assumption, unfortunately was an unusual and definitely a completely new assumption, but it had some key simplicity properties. It had some ideas why, for example, the sum of squares paradigm should not attack it, should not break it. But at the same time, it was unusual and new, and we did not know how to prove that these new pseudorandom objects are actually pseudorandom based on well-founded assumptions. And that's kind of how things stood until just a few months ago. And then, of course, the reason why I'm talking to you is that just a few months ago, just a couple of months ago, in our joint work, we were able to, in fact, show how to build I/O entirely from well-founded assumptions. And indeed, by means of this paradigm that we had been exploring, where we build a new pseudorandom object as the cornerstone for constructing I/O. And again, we do this based on 4 well-founded assumptions that I've listed here. I'm going to talk more about right now. So with that, I'd like to transition to the technical part of this tutorial. And I'm going to begin by talking about the first of these assumptions, namely the LPN over ZP assumption. Okay, so let's jump straight into that. So the LPN over ZP assumption within cryptography has quite a long history. It was first proposed by Blum et al. Back in 1993, and then proposed, and that was proposed in the context of P equals 2. And then it was proposed in the context of general prime fields in a joint work with Yuval Ishai and Manoj Prabhakaran back in 2009. But really, this assumption, this LPN over ZP assumption, actually has a much longer history and dates back to concepts from the 1950s, namely the concept of random linear codes from error correcting coding theory. Okay, so what is a random linear code? A random linear code is defined by a completely randomly chosen matrix A that we show here. This matrix A has n rows and L columns. Okay, and if we want to encode a vector S, an L-dimensional vector S, all we do is multiply our matrix A with this message S, and that yields a code word C. Okay, and that's it. The fact that it is described by a matrix and matrix multiplication is why we call it a random linear code. Okay, and these codes again were studied in the 1950s, and in fact, they were shown to exhibit quite strong, in fact, remarkably strong combinatorial error correction capabilities against sparse error. This is the classic work of Gilbert and Barshamov from the 1950s. So in our context, what does that mean? It means that we're going to pick a n-dimensional vector E that is very sparse. So it's 0 almost everywhere, but with probability 1 over L to the delta for some constant delta greater than 0. It can be arbitrarily close to 0. For example, 1 over the 10th root of L. With that probability, a particular position of E, some particular position EI, will be simply chosen at random from ZP. Okay, and that's how we sample this very sparse vector E. Okay, and now the problem of decoding such a noisy encoding would be to take AS plus E and recover S, right? And again, what was known was that known from the 1950s, is that combinatorially, it is always possible. It is possible with overwhelming probability to actually recover S from such a noisy version of the code word. However, despite the remarkable error correcting capability of random linear codes, in all the decades since the 1950s, no efficient decoding algorithm has been found for this context that I'm describing right here. Again, despite decades of study. And here what we mean by efficient is just something that is sub-exponential in the dimension L of the vector S. Okay, and I'll make that even more precise just right now. So more concretely, what we're assuming is that there exist arbitrarily small constants, epsilon and delta greater than 0, such that no time 2 to the L to the epsilon adversary, so sub-exponential in L, specifically 2 to the L to the epsilon time adversary, can distinguish between AS plus E, as I just described, and a completely uniform vector U, okay? And it turns out that even though here I'm asking for indistinguishability, there's a well-known search to decision reduction that, for example, you can find in the work of Michiancho and Moll from 2011 that shows that, in fact, if it is sub-exponentially hard to recover S from A comma AS plus E, then in fact it is sub-exponentially hard to distinguish between AS plus E and a completely uniform vector of dimension n over ZP. And indeed, this, as I mentioned, this problem has been studied quite extensively. And all we are assuming is that it is secure against 2 to the L to the epsilon adversaries for any constant epsilon greater than 0. But in fact, the best known attack runs in time 2 to the order L to the 1 minus delta. So there's actually a very substantial gap between the best known attack and the running time of the adversary that we're assuming. And just to talk about what I mean by the best known attack, in fact, as this slide that I've borrowed from Geoffroy shows, there's actually a staggering number of papers that have been written over the last many decades on attacking this assumption, on trying to decode noisy random linear on code words that are generated from random linear codes. And and again, despite all of this work, the best known attack, again, is 2 to the L to the 1 minus delta, where all we're assuming is 2 to the L to the epsilon. And so that is the first and in some ways sort of the most interesting of the well-founded assumptions that we are relying on to construct I/O. And indeed, this assumption has been also used in cryptography many times. The version that we're making is quite weak. In fact, a stronger version of this assumption, where delta is greater than 1/2, was used to build public key encryption. But we are not making even that strong an assumption, even though that assumption also has never been attacked, also by quantum sub-exponential adversaries. So all we're assuming, again, is that this holds for any constant delta greater than 0 and for any constant epsilon greater than 0. And I'll just mention that we can reformulate this assumption, not in pictures, but in mathematical language, by just saying that what we're assuming is that if we look at these random vectors AI from ZL, from ZP to the L, together with AI inner product S plus EI, then this distribution is computationally indistinguishable against 2 to the L to the epsilon adversaries from the distribution that corresponds to just the vectors AI and completely uniform values from ZP UI. Okay, so that is the assumption that we are making. All right. So why are we making this assumption? Indeed, you'll hear much more about this later on in the tutorial, but I thought I would gently introduce sort of the technical types of arguments that we're going to be making in the remainder of this tutorial to build IO by showing you just sort of a little preview of how we use this LPN over ZP assumption. Okay? And as I mentioned before, our new work crucially builds a sort of new pseudorandom object along the way to building IO. And indeed, it is improving the pseudorandomness of this new object that we use the LPN assumption. Okay? And actually, we use it in a very simple way. And it is really at the heart of our work to use LPN over ZP to build this new key pseudorandom object. Okay? So this pseudorandom object, again, is based on our previous work that started in the joint work with Anant and Jane, and the work of Lynn and Matt, and several follow-up works. And as I mentioned before, it's a little bit of an unusual pseudorandom object. So let me kind of tell you what it is that this object computes, and what makes it a little unusual. So I'm just going to describe to you in this initial warm-up phase just the output of the pseudorandom object. I'm not going to talk to you about how we compute it. You'll hear more about that in part 3 of the tutorial. So the output of our pseudorandom object actually has two parts that are unfortunately correlated in sort of an unusual way. Okay? The first part looks a lot like the distribution we just saw from LPN over ZP. So the first part consists of these random vectors AI, together with the inner product of AI with S, plus EI, that's chosen from the sparse distribution as I just described, but then also plus XI, where XI is just a uniformly random bit, 0, 1. Okay? And so far so good. This is sort of the first part of the output of our pseudorandom object. But where things get a little funny and a little different from before is that the second part of the output is the output of a classic pseudorandom generator on input these xi's, so x1 up to xn. So we think of x1 up to xn as the seed to our classic pseudorandom generator, and we also output that. And so again, what makes this a little unusual is that, of course, everyone who uses a pseudorandom generator is taught that you don't mess with the seed, right? You use the seed only and exactly to compute the pseudorandom generator, and then you throw it away. You never touch it again. But in this case, we're not following that advice. Instead, we're choosing the pseudorandom seed, x1 up to xn, but then we're reusing it in the first part of the output of this distribution, where we're kind of using it also as the noise to hide the inner product of ai.s, in addition to the LPN noise, right? And looking ahead, two aspects of LPN over ZP will be critical to us here. I'm only going to really touch on the first and simplest aspect right now in this sort of initial warm-up stage, just to give you a sense of what type of arguments we have. And it's a really simple argument. So what I'm going to show you now is that by using LPN over ZP, we are actually able to prove that this output that I just described, this two-part correlated output, is pseudorandom. And again, this was where we were stuck for years before. We had these new pseudorandom objects that had some kind of correlation, but we didn't know how to prove they were pseudorandom. Here, this is different. We've modified it in a way that uses this LPN over ZP, but now we're able to prove that it's pseudorandom in actually a really, really simple way, which I'm about to tell you, okay? So we need to show this is pseudorandom. What do we do? Well, first we just observe that if we look at the beginning of the left-hand side of this distribution, it actually looks exactly like LPN, right? We see AI, AI.s plus EI, which is exactly what we saw in the LPN distribution. So we can use the LPN assumption to immediately argue that this, the output of the pseudorandom object is actually computationally indistinguishable from AI, UI plus XI, together with the output of the PRG. So why is that? Well, I'm going to give you a really quick reduction that shows that if there was an adversary, a sub-exponential adversary, that could distinguish between these two distributions, then it could also break the LPN assumption. Why is that? Well, I'm going to make an adversary for the LPN assumption that gets an LPN sample. It either gets AI, AI.s plus EI, or it gets AI, UI, right? And then what the reduction does is simply choose x1 up to xn itself, add xi to the corresponding part of the sample it received uh, from the LPN adversary, and then we just compute PRG on our own, because after all, we chose x1 up to xn on our own, right? And in this way, we either construct the distribution above, or we get the distribution below, depending on whether we started with an LPN sample or a uniform sample. And so in this way, we show that any adversary that can distinguish the first distribution from the second distribution could in fact break the LPN over ZP assumption, right? So this is a very simple idea, and it immediately means that we can replace AI.s plus EI with a completely uniform value UI, right? And now we just have a trivial observation that if I have a uniform value over ZP, and then I add a random bit to it, I still have a uniform value over ZP, right? So just the distribution AI, UI plus xi is identically distributed to AI, UI. There's just no difference between these two distributions. So we can now completely eliminate x1 up to xn from the left-hand side of this distribution. And having done so, now we've gotten rid of the correlation, right? There's no longer any use of the seed to the PRG, x1 up to xn, except as a seed to the PRG. So now we can simply use the pseudorandomness of the PRG and immediately get that the original distribution is indistinguishable from just a completely random distribution where AIs are random, UIs are random, and this capital R is random, and just replaces the output of the PRG, right? So again, in this very, very simple way, we're able to use the LPN over ZP assumption to sort of break up this annoying dependency that used to be there in the earlier works, although in a slightly more complicated form. Here we were able to simplify it. And therefore, we're able to prove pseudorandomness, even though we did have this dependency where x1 up to xn was being used both as a seed to the PRG, as well as some sort of noise to hide the AI.s portion of the left-hand side distribution. Okay, and that's it. This is like this very, very simple argument that is the only way that we ever use the actual assumption of LPN. The actual assumption of indistinguishability is only used in this very, very simple way in our construction. Okay. All right, so that's a little bit of a preview. As I mentioned, though, we do have other assumptions that we make. So let me talk to you a little bit more about that. So the other assumptions that we make, the first one is called the learning with errors assumption, or the LWE assumption. And it's actually exactly the same as the LPN assumption that I just gave, except that instead of these errors EI coming from a sparse distribution, a sparse sort of Bernoulli distribution, instead they come from a small Gaussian distribution. So each EI is chosen independently to just be a very small value compared to P. So a much, much smaller value than P, but the error is not sparse, it exists everywhere, okay? And this type of assumption we make with what's called a sub-exponential modulus to noise ratio, which means that the magnitude of EI is sub-exponentially smaller than the magnitude of the prime P, okay? And indeed, this assumption, LWE, is a well-trod assumption in cryptography. In fact, it's known to be true if the shortest vector problem over general lattices is worst case hard to approximate to any sub-exponential factor. This is the beautiful classic Gödel Prize winning work of Regev and followed up with the work of Pikert and Bukursky et al. So really beautiful worst case to average case reductions that are known for LWE. In fact, also the same search to decision reduction that I just mentioned for LPN also applies to LWE. That was also observed in this work of Michianshu and Moll back in 2011. And indeed, LWE has turned out to be a really remarkably versatile assumption in cryptography and it is most famously being used for constructing fully morphic encryption in the breakthrough works of Prekursky and Bhakuthanathan, and also some joint work with Gentry and Waters. Um, and and so LW is sort of a well-trod assumption in cryptography. Now, I'm hoping that some of you who are watching and listening may have noticed something, which is that I mentioned that LW is just like LPN. It's also assuming that AS plus E is indistinguishable from random, from UI, right? The only difference is the distribution over the errors EI. Let's think about the analysis we just saw, right? In fact, if you think about it, there was nothing special about the LPN distribution that we used in this analysis, right? We could have just as easily worked with LWE, where all those errors EI would have just been small instead of sparse. So indeed, in the proof of pseudorandomness, we're actually not using anything specific to LPN. That proof could have just as well worked with LWE. But nevertheless, LPN is at the heart of our construction. And that is because the sparseness of this error EI turns out to be crucial for suitably computing the pseudorandom object that I haven't described, the computing aspect of it, right? I've only described to you the output of the pseudorandom object. And for details on that, stay tuned. You'll find out much more in part 3 of this tutorial, which Ayush will give. And this is sort of my little ad for that to encourage you to see really how crucial a role that it plays. Okay. So that's the LWE assumption. We also make 2 additional assumptions. The first is the assumption that PRGs, pseudorandom generators, exist that are computable by constant depth circuits, NC0 circuits, that achieve just any polynomial stretch. That is, if the seed is of size n, is an n-bit string, then the output of the PRG is an n to the 1 plus epsilon bits length string for any constant epsilon greater than 0. Okay, this is again an extensively studied assumption, starting with sort of the seminal work of Goldreich back in 2000 and the work of Krein and Milterson in 2001. This has been extensively studied and cryptanalyzed, and also used in a number of different cryptographic uses. First used in cryptography in a joint work with Yuval Ishai, Eyal, and Raffi Ostrovsky, Eyal Koshulevitz and Raffi Ostrovsky back in 2008. And again, many, many other papers. And then finally, we also assume what's known as the SXDH assumption over bilinear maps. That has also been extensively studied and used since its introduction in 2005. I won't bother to define that in any detail because, again, it won't be important for the rest of the tutorial. We're just going to use it as sort of a black box from previous work that exploits that assumption. And again, all of these assumptions we make with respect to sub-exponential time adversaries. Again, that is against an adversary that runs in time 2 to the n to the epsilon for a suitable security parameter n, and just for any arbitrarily small constant epsilon. Okay, and this is well supported by the years of both application and cryptanalysis that has been done in these other assumptions. And with that, I will conclude this first part of the tutorial. Thank you for your attention and for watching and listening to me. Let me give you a quick idea about what you're about to see. So in part 2, Rachel will show us how we get to I/O starting from just a few basic ingredients. In particular, a certain type of functional encryption, which she will define, an object related to fully morphic encryption that follows from LWE, again, that she'll talk about, and this key new pseudorandom object that we call an SPRG, a structured seed PRG. Okay, so she's going to show you how we start with those things and get us all the way to I/O. And then finally, in part 3, Ayush will show you how we can use LPN over fields and PRGs in NC0 to actually build this key pseudorandom object, Again, I showed you the rough idea behind why it is pseudorandom, but the actual construction of it crucially uses the sparseness of the LPN error, and you'll get a chance to learn more about that in the remainder of this tutorial. Thank you again, and that concludes part 1 of the tutorial.